All right, 6.3, let's talk about binomial random variables. Okay, so we did the whole thing with the basketball free throws in class, and that whole situation was a binomial setting. Okay, let's talk about why. To be a binomial setting, we have to have four conditions, and all four of them have to be met. All right, so it has to be binary, meaning there's either success or failure. So for each free throw, he either made it or missed it. Independent, each trial must be independent, okay? Making or missing one free throw has no effect on your ability to make or miss the next one. Okay, number, the number has to be fixed in advance. So we knew he was going to shoot 3 free throws no matter what. And then the same probability, okay? It's the same on each trial. A way that you can remember that is bins. Okay, so for binomial, we have to check the bins. Is it binary, independent, fixed number, and same probability? Okay, so let's see if this is a binomial setting. Genetics says the genes children receive from their parents are independent from one child to another, and each child of a particular set of parents has 0.25 probability of having type O blood. Suppose these parents have 5 children, count the number of children with type O blood. Okay, is this a binomial setting? Well, let's go through. Bins, so B, binary. Yeah, they either have type O blood or they don't. Is it independent? Well, they told us, all right, that the genes they receive are independent. Number, we know that they're going to have 5 children. And then is the probability the same? Yes, we know it's 0.25. So this is a binomial setting. All right, here we have another setting. We're going to shuffle a standard deck of 52 cards, and we're going to turn over 10 cards one at a time and record the number of aces. Okay, so let's go through. Binary. Yes, either it's an ace or it's not. Independent. Here's the issue. No. Okay, these events are not independent because every time once I turn over the first card, I have changed all of the probabilities for the next 9 cards. Okay, so this would not be a binomial setting. Okay, so now I want you to try this one. Okay, so this setting would not be binomial because we didn't have a fixed number of trials. We're going to keep turning cards over until we get an ace. All right, so that is not a binomial because we have to have that number set in advance. All right, so calculating binomial probabilities. We already talked about this in class. But you're going to want to make sure in an FRQ situation that we are specifying. So you have to say, this is a binomial random variable. The number of trials is this. The probability of success is this. Okay, so we have to make sure that we are clear about those things. And we'll look at an example. And then we got to perform calculations. So you can either use the binomial probability formula that we came up with in the free throw activity, or we're going to talk about using the calculator commands. All right, and then the last thing is make sure you answer the question that was asked. So don't just give me a number, put that number in context. Okay, so let's look at an example. Same setting as before, where we have the children with type O blood, and we want the probability that x equals 3, or that the number of children out of the 5 that they have would be 3 of them having type O blood. Okay, so if we use our formula, it would be plugging in things like this. All right, so we say x is a binomial random variable that with n equals 5 and p equals 0.25, that satisfies our step 1. And then we show our work plugging all those numbers into the formula. And then the last step is to answer the question in context. We would say there's about an 8.8% probability that exactly 3 of the 5 children have type O blood. All right. Now, this is not bad, but the less things that we have to type into the calculator, the better. So let's look at using the distribution that's actually in the calculator for you. All right, so when we want the probability of exactly some number, so in this case, x equals 3, you're going to use, if you're on a Casio, it's BPD. If you're on a TI, it is binom PDF. All right, so let's look at where these things are. So it's going to be in the same section of your calculator as like the normal CDF when we did the normal distributions. Okay, so on the Casio, you're going to go to menu and choose stat. And then under the distributions, last time we picked normal, this time we're doing binomial. So it's going to be F5. Okay, and if we want X equals a number, it's going to be BPD. All right. Yours might look like this when you first click on it. We got to change it from list to variable. So hit F2 and then you'll be able to type the things in. So we're looking for X to be equal to 3. We have 5 trials and the probability is 0.25. On the TI, everything's in that distribution menu. So second distribution, it's all the way at the bottom. So it's actually easier if you just scroll up. And there's Binomial PDF. That's the one we want. And then we're going to type in our information. So it would be 5 trials. The probability is 0.25. And then the X value that we're looking for is 3. Okay. And then we're going to hit that. And over here, I would just hit enter. Okay. And then there's our probability. And that matches what we got when we used the formula. Okay. So same scenario, but this time we want to know what's the chances that they have more than 3 children with type O blood. Okay, so that is the probability that X is greater than 3. So in this scenario, that means either X equals 4 or X equals 5, and that's why we're adding those two probabilities together. Okay, so you would have to do, you'd have to plug in for the probability of getting 4 children plus the probability of getting 5 children, and we're going to add those two probabilities together. All right, this one is not that bad because it's only 2. But imagine, you know, in this case, let's say they had 9 children and we wanted the probability of more than 3. We would have to do 4 and 5 and 6 and 7 and 8 and 9 and add all of those together. So again, this is going to be another scenario where the calculator is just going to make things so much easier for us. All right, something that is important to know, anytime we want, you know, greater than, less than, whatever, something that's not an exact value for X, we're going to use BCD or binomial CDF. Okay, now the calculator, whatever number you put in for X, the calculator is going to find the probability that X is less than or equal to that number. So if this couple has 5 children, okay, let's think about the possibilities. 0 of them could have type O, 1, 2, 3, 4, or all 5. Okay, the problem is asking us for the probability that X is greater than 3. That means we want these two. All right, but the calculator only finds less than or equal to probabilities. All right, so if I put 3 in, the calculator is going to find this probability. Okay, something that we know from the past is all of these together, all these probabilities together have to have a sum of 1. So if the calculator gives me these, but I'm looking for these, then 1 minus that number will give me the answer that I am actually looking for. Okay, so you have to pay attention to what the problem is asking for, because your calculator is always going to do less than or equal to whatever number you put in for that X value. All right, now this time it's BCD or binomial CDF. All right, it's right next to binomial PDF and BPD in the calculator. So you're going to the same place, just make sure you pick the C instead of the P. And then in this case, because we want greater than 3, and the calculator is going to give me less than or equal to 3, I'm going to do 1 minus that number that the calculator gives me. Okay, so there's an extra step here whenever I'm doing these greater than probabilities. Okay, so we're just going to do one last example. I want you to pause here, read through this, and you try it on your own, and then we'll come back and talk about the answer. Okay, so this one may be a little tricky. We have a binomial distribution, okay? We want the probability that fewer than 10. So we want the probability that y is less than 10, all right? But my calculator can only do less than or equal to. So the X value that we need to put in is 9 because less than or equal to 9 is the same thing as less than 10. And the calculator only speaks in less than or equal to. So if you put 10 in for your X value, the calculator was finding the probability of 10 or less, which is not the same thing as less than 10. All right. And then one more. All right. Same scenario. Okay. But let's say that they actually did it and only 9 customers won a free lunch. All right. Would this give evidence that the computer program is flawed? All right, and so the probability of only getting 9 or getting less than 10 is 0.006, okay? In other words, 0.6%. That is extremely low, and I would say that is convincing evidence that the computer program is flawed and it's not really operating at the same probability that it claims to. All right, that's it for this part of 6.3.